Hello. So once we have our dose profile or the information on how to calculate the daily dose, it is important, as we have already talked about, that the dose is related to a certain concentration, but that certain concentration we are not exposed to all the time. So we will look at the things about time activity profile, and then further we will see how to do a risk assessment from inhalation. So what is the relation is on the time activity pattern and our exposure. So each day a person may spend different amounts of time in different locations. So first, the location itself is different. We can be in a house, we can be in an office, we can be in a indoor like a transport vehicle, which is enclosed environment, or we can go for some recreation in a gymnasium. Now within these locations also there are these sub locations. For example, we have our house. In house we can have kitchen, we can have a bedroom, we can have living room, washroom, then we can have dining room. We can have also a mini office inside the house, like a working room or a study room, which may have different furnitures and which may also have things like printers and copiers. So within the house itself, there are so many locations, as we have actually talked about time and again, and which is the central aspect of the complexities of the indoor air exposure. Then in the office again, we can have a office cabin where one person is sitting or maybe two-person. Then we also have like cubicles, which are semi-enclosed areas, because at certain point the cubicle will give us some privacy, but the top part of the cubicle is open and is shared among many people. So it is a sort of enclosed but not enclosed area. And we may also have a open concept office where you have a lot of tables and chairs and station office material, and it is completely different. Washrooms in offices will be much more utilized than washroom in the kitchen. In offices, there may be separate coffee room or a canteen which is not basically completely open to the outdoor air. It may be sort of an enclosed canteen. Then we may have a copier room or like a printing room. So that will have another kind of exposure pattern associated with it, and people who are in those kind of rooms will have different exposure than people who are in their private cabin or people who are sharing a cubicle or all the service staff. And there may be a storeroom also where a lot of cleaning materials will be saved, will be stored, and since it is a office, there may be a lot of cleaning material that will be stored, and the person who is cleaning will have a completely different exposure profile. Then we may have a gym where you can have lot of people in a closed environment. The temperatures are probably warm or not warm because AC is running, but how good is the circulation of the AC? People are sweating, so they are releasing different sweat, then they are exhaling, so different chemicals, they are inhaling a lot. So whatever the contaminant or whatever the substances there in the gymnasium, people will consume or inhale that substance to a substantial proportion, to a substantial amount. At the same time, now people are, when they are exercising, working out, they are exhaling a lot as well. So the indoor microbials are also going out at a much higher rate than the normal rate. Also, people will be sweating and this some microbes, and then they are moving around a lot. So maybe this vigorous activity will also help to increase or would lead to an increase in the emissions of microbial burden also. So in summary, each place will have its own concentration of a contaminant. And a person does not always live in a gym, a person does not always stay in a cabin or a cubicle, a person does not always stay in a kitchen, a bedroom, a living room, a washroom all the time. Right? We will be in like maybe 1 hour, 2 hour in the kitchen to a person who is for a person who is cooking. Then the person may be in the bedroom, person may be in the living room for some time, washroom for some time. So then the question is, how do we define the effective exposure concentration? So what concentration do we use if we have to conduct the risk assessment now? And risk assessment in terms of exposure every day or exposure every hour, but we need to have what is our effective concentration. So effective concentration or exposure concentration, similar to the average daily dose, we can calculate this effective or exposure concentration. So ECI, let us say each place will have some effective concentration or sort of averaged concentration that we will derive to get the total exposure concentration. So let's say this is our effective total exposure concentration. And this is the effective concentration for location I, location activity. So for stay at each activity. So this is our effective concentration for stay at each activity, and each activity will contribute something to the overall average effective total exposure concentration. Now what is the effective concentration for each activity? It is as follows. This Ci is the concentration. So let's say this Ci is the concentration at the location I. So let's say concentration in the kitchen. Then ETI is the time, exposure time we will spend in that location, in location I. So again 2 hours per day in a kitchen, let us say 1 hour in the washroom, something like that. Then this is the day to hour conversion. Then frequency, how many days per year. So maybe in reality, maybe someone spends except let's say 10-20 days, all other days. For 330 days, let us say, or 340 days, a person will be there in the kitchen 340 days out of 365 days, let us say 25 days were break time. So this is our exposure frequency, and then exposure duration 20, 30, 40 years, whatever duration of time, and this is our average time in days. So generally for non-cancerous, we will come to that. So this will be our generally how many days, what is our actually averaging time. So is it the same time as our exposure time, or is it the same time as something else? So I will write a question. So either it is the exposure duration or something else. So I hope it is clear that the effective exposure concentration for any location would be basically in proportion to the time we spend in that location every day, in a way. Assuming every place we are frequenting to the same amount of time every year. Otherwise, it's a function of the concentration, the exposure time every day, exposure frequency, how many days per year, and then exposure duration, how many years are we inhabiting that, frequenting that zone, divided by the averaging time in days. So if a person spends time in 4 places in a day, so let us say kitchen, bedroom, living room, and let us say one office, and everything else is zero. Or let's say a person is staying indoors for several years or couple of years as a thought process. So then if a person is inside the day for 2 years, let's say lockdown. So a person is in a room for 2 years, and for the person might be spending 2 hours in kitchen, 8 hours in bedroom, 6 hours in living room, and so on. Sometime in dining room, or maybe 10 hours in living room. So if a person spends time in 4 places in a day, then I equal to 4, because we have 4 stay. And if this happens for the same number of days every year, actually, for the same number of same number of days every year, so ever for the same exposure duration. So okay, same number of hours, same exposure duration is every year. So a person spends same hours every day, let's say, or even if it changes, as long as for a thought we will do per hour, let's say hours here. So 4 hours kitchen, 4 hours living room, 4 hours bedroom, 10 hours TV room, something on that sort that adds up to 24. Or let's say 4 hours in kitchen, 10 hours in living room, 14 hours, 8 hours in bedroom, 2 hours in dining room. So the sum of all 4 exposure times should be 24 hours, because a person cannot spend 24 hours a day. The limit is 24 hours. So if the person is repeating same pattern every day, then the exposure time, the sum of exposure times in those patterns should be 24. Or maybe spend 1 hour less in kitchen, 1 hour more in the living room, or 1 hour more in the bedroom. But the activities, if you are doing 4 activities per day, then that exposure time in all those activities should be 24 hours, because we have divided 24 hours of a day into these 4 activities. Or if there are 10 activities in one day, the time spent in 10 activities should be equal to 24 hours. Otherwise, there is a problem in our expressing the problem. So any activity, sum of all activities in a day, sum of exposure times for all activities in a day cannot be more than 24. Actually, it has to be exactly 24 hours. So any day, if you add exposure times for any activity or all the activities carried out in a day, the total time should be 24 hours. Now let us say we have done this exposure, effective exposure concentration. Then the next thing comes is assessment of the risk. So we know the concentration a person is exposed to. What is the risk to health? So I am going to explain one such type of definitions, and the viewer is free to look at other definitions and other values reported by several agencies possibly. I am going to explain one of them. So these kind of risks can be expressed as a reference concentration. A reference concentration is basically these are defined by the US EPA integrated risk information system. So a reference concentration is an estimate and with uncertainty spanning perhaps an order of magnitude of a continuous inhalation exposure to the human population, including sensitive subgroups, that is likely to be without any appreciable risk of deleterious effects during a lifetime. What it means is, let us forget about the uncertainty right now. What it means is, if a person, let's say reference concentration is 1 microgram per meter cube. So if a person inhales this 1 microgram per meter cube air for the entire lifetime, it is likely to be without any appreciable risk of deleterious effects. So a person is not likely to develop any health effects. The key is not likely to. The definition does not say the person will not develop any deleterious effect, or definitely it's not saying that the person will develop. It is also not saying that a person cannot develop a deleterious effect if the concentration is below my reference concentration. The definition is that a person is likely to be without any appreciable risk, and it is also not saying zero risk. It is saying no appreciable risk of deleterious effect and likely to be with no appreciable risk. So it is the term is in a probabilistic sense. It is, the definition is not giving a hard yes or a hard no. It is saying it is likely that there will be no appreciable risk, because every person has a different physiology, a different setup in the body. So some people maybe maybe some people develop, but the chances are that it may not happen. It will never say that definitely it's not happening. It may not happen. The person may not have, or the person does not have, or no, a person likely does not have a appreciable risk of deleterious effect. So it's a bit tricky definition in that it is defined in a probabilistic sense. So it is an estimate, let us say 1 microgram per meter cube. The next important part is uncertainties spanning perhaps an order of magnitude. That means around factor 10. So if the value is 1 microgram per meter cube, which is defined as the RFC, if say example RFC is defined as 1 microgram per meter cube, 1 order of magnitude uncertainty means it can be from 0, I'll just write it here, from 0.1, which is 1 by 10, to 10 micrograms per meter cube. It can be any of these value possibly, which is 1 multiplied by 10, and our RFC is somewhere here. On a log scale this will be our RFC, which is of 1. I will write units here. So the RFC is 1 with uncertainty spanning perhaps an order of magnitude. So uncertainty means the actual value is possibly between 0.1 and 10 of a continuous inhalation exposure. So a person is inhaling this air continuously, and this includes sensitive subgroups, that is likely to be without any appreciable risk of deleterious effects during a lifetime. So if a person lives in this environment for a lifetime, the person is likely to be with no appreciable risk of adverse effects. Then the next is inhalation unit risk. This is generally this is used to basically evaluate our cancer risk. So IUR is an estimate of the increased cancer risk from inhalation exposure to a concentration of 1 microgram per meter cube for a lifetime. So again, if we say if a person inhales 1 microgram per meter cube, how much is the increase in the risk of the person to get cancer? The IUR can be multiplied by an estimate of lifetime exposure in microgram per meter cube to estimate the lifetime cancer risk. There's a repetition, but never mind. So if you multiply our EC, let's say effective concentration over a lifetime, into IUR, we will get lifetime cancer risk. So effective concentration averaged over the life multiplied by IUR would be the lifetime cancer risk. So these two are quite used for inhalation. This can be used and this can be used, and for cancer we will basically average the for lifetime exposure. There is another term called reference dose, which actually also includes which includes oral exposure, meaning ingestion and water. But we will look at here for sake of completeness. An estimate, perhaps with an order with uncertainty spanning perhaps an order of magnitude of a daily oral exposure to human population, including sensitive subgroups, that is likely to be without any appreciable risk of deleterious effects during a lifetime. So basically it is the same. The definition is pretty much the same as the reference concentration, except now we are talking about daily oral exposure, and in the reference concentration we had the continuous inhalation exposure. So how much is person is eating every day or drinking every day certain substances. Here it was how much a person is inhaling the air inhaling the air over the exposure duration. Inhaling the air over the exposure duration. So reference concentration and IUR. So non-cancer risk is generally calculated to estimate our estimated using reference concentration. So hazardous quotient. Here we will have hazard quotient. For non-cancer risk, we will have a hazard quotient HQ, which will be C air adjusted, which is basically same as our effective concentration total. Which is summation over I ECI divided by the reference concentration. So how does our equivalent concentration compare with the reference concentration? For oral, we will have ADD by RFD. So for this course, we are not going to do this, but we will do this EC total or CR adjusted by RFC. The CR adjusted would be total. So again, this will be like summation. So same as EC total. So that's our hazard quotient, and we will do an example so that this becomes clear. For cancer, we have again, so this is our EC. We will do EC total instead of C adjust error. So risk will be EC total multiplied by IUR. So this will tell us the risk. This guidance is through the Agency for Toxic Substances and Disease Registry. The website is here. This is sort of a theoretical risk, this risk value. Now, if this risk value is less than 10 to power 6, that means less than 1 person in 1 million person similarly exposed will develop cancer, which means if 1 million people, if 10 to the power 6 people were exposed to the same air, less than 1 person will develop cancer. A risk greater than 10 to the power minus 4 means more than 1 person in 10,000 persons similarly exposed will develop cancer, which means if we had 10,000 people, there is some polluted air and the risk is 10 to power minus 4 and there are people in polluted air. In 10,000 people, more than 1 person will develop cancer if the risk is more than 10 to the power minus 4. If the risk is 1, that would mean everyone who is exposed to that air over the lifetime will develop cancer. So the exposure also has to be averaged over the lifetime. Importantly, we should know that the concentration is averaged over the lifetime. EC total, this is averaged over lifetime, as we recall from previous slide. So for averaging time is basically over lifetime. For cancer, we are going to average our exposure concentration over a lifetime. So 10 to power minus 4 risk means if 10,000 people are exposed to the same air, one will develop cancer. The guidance again is as like this, that if the risk is more than 10 to the power minus 4, there is a concern for increased cancer risk. If the risk is less than 10 to the power minus 6, if less than 1 person will develop cancer in 1 million people. So this is qualitative judgments or qualitative guidance or qualitative suggestions written in these in this area. But if we read this, these are basically judgmental based risk, and of course a person, a policymaker can decide, no, I don't want, for me even 10 to the power minus 6 is not of no concern, I want to make it 10 to the power minus 6. So okay, so but these are judgment based. So as a reference, it is given, okay, no concern for increased cancer risk if the risk is less than 10 to the power minus 6. There is a concern if a risk is 10 to the power minus greater than 10 to the power minus 4, and could be a concern if the risk is between these two values. So this is again judgment based decision, that which number do I say is of concern to me. There are repositories. So the next thing is, we should, to calculate risk, we need reference concentrations and we need IUR. So again, so we need these values to calculate our risk. So some online repositories are available. I will highlight one, but like again, the interested person can search more repositories and more guidance values which are given by different agencies. So here because this was probably very easy to find, there is this integrated risk information system which is developed by the US EPA or hosted by the US EPA. And here we can have the chemical name, if reference dose has been assessed, if the reference concentration has been assessed, if the carcinogenicity has been assessed for the chemical. So this is the information that is there, and then we can click on the chemical and get the individual reference risk. Okay, so here what has been assessed, and here we can have different options that we want as here. So which thing we want to check, cancer risk or non-cancer risk for oral routes or inhalation routes. We can even choose the systems organs affected as per the database. Cardiovascular problems or dermal problems or developmental problems or endocrine, gastrointestinal, hematologic, hepatic, immune problems, musculoskeletal problems, nervous system problems, ocular problems, reproductive effects, respiratory effects, urinary effects, or even other. So we can check what systems we want to do and see if information is available. For then we have non-cancer toxicity for oral, so reference dose, or inhalation, reference concentration. Then what are the uncertainty factors associated with this? Then these are some guidelines for different years and depends which year we want to include. Then we have our inhalation unit risk, which is IUR, and oral slow factor for the oral ingestion for cancer toxicity. And as you can see, there is also a lot of chemicals. So we have here our organic chemicals as well: acetone, arachror, aldehyde carb. So these are pretty much all organic chemicals. Here we had acetaldehyde, which of course is a chemical which can be found in indoor air, and if we go acetaldehyde, oral not done. So oral ingestion assessment has not been done. But for inhalation, RFC, so non-cancer risk can be done. This assessment has been done, and the carcinogenicity assessment also has been done. And last revised RFC assessment, inhalation risk assessment for non-cancer risk, done in 1991, for cancer risk done in 1998. So organic chemicals are there. Also, element or inorganic substance are also there. Chromium 3 salts, chromium 6, copper cyanide. Then we have free cyanide. So these are organics, and copper, here you can have copper and chromium salts, chromium 6. So inorganics as well. And you have oral assessment also. Here it's under discussion, looks like, and this has been done. Chromium 6, yes. So RFD assessment done, RFC assessment done, and IUR assessment also done. So now what we did is you can also get the values now. So basically I just checked that we want to get cancer, non-cancer risk and cancer risk. So as we started clicking these check boxes, and for the inhalation route exposure only, and then we get these values. So here, for example, acetaldehyde assessment type, there was a cancer risk assessment. Then there was critical effect of tumor that was checked. Some characterization, the value that is available for us to check, IUR, inhalation unit risk, and it is 2.2 10 to power minus 6 per microgram per meter cube. So then we know, okay, for acetaldehyde, we have the cancer risk IUR 2.2 10 to the power minus 6 per microgram per meter cube. For acetaldehyde, we also have the non-cancer assessment done. Degeneration, the critical effect is degeneration of olfactory epithelium. And here we have the value of reference concentration to check our values, our observed or actual values with. We also have this reference concentration, 9.9 into 10 to power minus 3 milligram per meter square. So this will become 9 micrograms per hour, 9 into 10 to power minus 3 milligrams per meter cube, which will become 9 micrograms per meter cube. So for acetaldehyde, we have the cancer assessment and toxicity value in IUR given. For acetaldehyde, we also have non-cancer assessment and RFC value is also given. So we have looked at the chemical risk assessment. We will look at little bit on the microbial aspects also. So one of the method is this quantitative microbial risk assessment, which tells us the probability of infection from a pathogen. So we will basically have a micro area where we have a lot of microbes in the air, or whatever amount of microbes in the air, maybe a particular species we are looking at. So that would be the concentration of pathogen in air in colony forming units per meter cube. So how much of that colonies are we going to inhale? That will be our dose. If we see in these in terms of units, we have CFU per meter cube multiplied by the inhalation rate, so meter cube per hour, multiplied by the exposure time. So how long have we been exposed to this microbe pathogen? So this is basically dose will be in colony forming units. How many colony forming units we are inhaling. The probability of infection is then given as a function of the dose and the survival probability of a single pathogen in CFU to the power -1. So this makes sense because we are inhaling so many pathogens in terms of the units that can form colonies. So we are inhaling these many and there is a survival probability of a single pathogen. So how many, this k times dose will basically is giving an indication of how many of these are going to survive. So and then the infection is then a function of how many of these pathogens are going to survive once they have been inhaled. So that is the thought, or that is the framework behind calculation of this probability of infection, which is given as this formula. So in summary, we have gone over the concept of risk assessment and exposure. We have seen daily average dose calculation, then how reference concentration can be used for non-cancer risk, and how inhalation unit risk can be used for cancer risk, and we have obtained an overview of quantitative microbial risk assessment. Next, we will do some examples.